All right, we're now recording, so let's start. First presentation is by Professor Onur Mutlu, who will be talking about RowHammer, RowPress, and beyond.
Okay, hello everyone. You can still hear me, right?
Yes.
Okay, great. Yeah. Well, good morning to everyone. It's at 1 a.m. here. I'm in California. Sorry, I couldn't make it. I'm normally in Zurich, but I'm on sabbatical these days. So I'm going to talk about some work we've been doing on Bitflips for a while. This is known as the RowHammer issue, but I think it's going to be broader than RowHammer going into the future. So I'm going to talk about issues like RowPress as well. I have quite a few slides. I don't think we're going to cover all of them. So expect that I will skip some slides, but feel free to ask questions, so you can interrupt me anytime. Okay. So when I actually introduce this topic to freshmen, when I teach at ETH or somewhere else, I actually give this image of this bridge. Do people know where this bridge is? Yes, okay. It's a Galloping Gertie. Basically, it doesn't exist anymore, actually. So if you said yes, maybe it's not perfectly correct because it was there. So this is what happened to it in 1940. And essentially, this in my view, this is a Bitflip on critical infrastructure. It's a robustness issue. And this robustness issue can cause all sort of other issues like safety, reliability, security, availability problems. I think of security very generally and robustness very generally. These folks are also sitting on some rod, which may be robust, may not be robust. If a Bitflip happens over here, these folks will not be happy very soon, essentially. I think the relationship with the infrastructure that we have today is quite interesting because that sort of infrastructure is very interesting, but it's not common. But if you look at the infrastructure that we're building today, we're going to be relying on the infrastructure, the computing infrastructure that we built. This is Mr. Bean with his self-driving car. Today, the self-driving cars are going to be a lot more interesting than this probably, but we will need to make them secure somehow. If a Bitflips happens over here, then we will have a lot of issues. So I think of security as preventing unforeseen consequences. You can criticize this as being very general, but I think this is what we're going to deal with going into the future. We really need to design robust systems that can deal with unforeseen issues like Bitflips that we're going to discuss. Okay, so what is RowHammer and what's the relationship? RowHammer is essentially the fact that you can predictably induce Bitflips in commodity DRAM chips today. And today, essentially, all chips are vulnerable. At the first time we tested, we figured, according to our experiments, more than 80% of the chips were vulnerable. And this is what's interesting about RowHammer is that it's the first example of how a simple hardware failure mechanism can create a widespread system security vulnerability. And if you know of something else that came before RowHammer, please let me know. I'm quite interested in these hardware issues that could actually lead to security, safety, and reliability issues. And people are writing articles like this that you may have seen. Let me give you some background on what we have been studying and how we actually looked at RowHammer and what's going to happen in the future, in my opinion. Basically, we've been looking at memory systems for a while from many perspectives. One of the perspectives is performance, of course, but performance is intricately tied to reliability issues in memory as well. So we've been arguing that memory is going to get much worse into the future in many aspects, and reliability is one of those aspects. And unfortunately, all memory technologies that we are dealing with today have this sort of issues. DRAM is clearly an interesting one because almost all computing systems have DRAM, and main memory is built out of DRAM. And if you look at DRAM, it consists of two main structures, which is one is the capacitor, which stores data, and the other is the access transistor and the access structures. And for this to work, both of these structures need to work reliably. If you actually reduce the size of the circuit so that you can store more data, you introduce characteristics that lead to more noise and reliability issues, and it becomes harder to make this work reliably. And this is the problem that we're dealing with. And if you don't like this picture, I don't like this picture necessarily. This is a logical view of DRAM. If you look at a physical view of DRAM, actually, this is fascinating. It's there's a lot of improvements that have been done inside the circuitry to make it actually high capacity. So we actually did a lot of studies on DRAM, and one of the type of studies that we did was actually to understand the memory errors that is happening in the field. We did this study with Facebook some number of years ago. I'll just show you one data point from the study. Essentially, we studied all of the memory errors that are in Facebook's fleet at the time, and we found out that the chip density, this is the DRAM chip density, that's employed in a server correlates quite strongly with the failure rate that you see in the field. Essentially, this is because denser chips are more vulnerable to noise, because cells are smaller and cells are closer to each other, that are densely packed. As a result, this manifests itself as errors in the system level, at the application level or system level, operating system level, etc. I don't have time to talk more about this, but you can take a look at the papers, etc. So we wanted to understand this sort of issues a lot more. So we built a lot of FPGA-based infrastructures to test DRAM memories. This is now open source, so you can take a look at it. We first open sourced as SoftMC, and more recently we released a DDR4 version of it, DRAM Bender, which can work with many different types of FPGAs actually, and we're working on building more prototypes. And the main reason actually we wanted to build this infrastructure initially was to understand these reliability issues. And one particular reliability issue is data retention. And if you look at DRAM cannot retain data forever or a long time. You need to refresh DRAM cells frequently. And this is actually one of the major scaling problems in DRAM. And we wanted to get rid of refresh. And that's one of the reasons why we built this infrastructure, to understand the retention time profiles of DRAM cells. And we basically wanted to measure the retention time profiles. I'm not going to bore you with the details over here, but most of the DRAM cells can be are strong. They do not need to be refreshed as often as 64 milliseconds. Today it's 32 milliseconds, and it's going marching down, let's say. But if you can actually understand the retention time profile of a DRAM chip, you could get rid of most of the refreshes. And that's actually been our goal initially. This is going to become important when we talk about RowHammer solutions, because RowHammer solutions are going to work against this. This is not that easy to do, actually. We wrote a lot of papers about it. I'm not going to talk about this in detail, but this is fascinating to me as well. We may get back to this later on. So while we were doing a lot of these studies, together with Intel, we actually did a lot of studies to understand read disturbance effects. Read disturbance is the fact that whenever you read a memory location or take an action to enable the reading of a memory location, you disturb other cells that are around you. In DRAM, it manifests itself when you activate a word line. When you activate a word line in a row in DRAM, you apply high voltage to it. And then when you actually, then you can read some data in that row after this. Now, if you want to read something else, you apply low voltage to this word line and essentially close it. This is called a pre-charge in DRAM. Now, in DRAM, if you keep doing this repeatedly, activate, pre-charge, activate, pre-charge, activate, pre-charge, high voltage, low voltage, it turns out if the chip is vulnerable, there are some cells, some vulnerable cells in adjacent rows that flip, that get corrupted. Basically, they lose their charge enough with every activate that eventually the charge gets depleted so that you cannot read it correctly. This is essentially data corruption, and we call this the hammered row. We call these the victim rows. And we basically demonstrated that more than 80% of the modules that we tested from 3 major manufacturers are vulnerable. And there are only 3 major DRAM manufacturers in the world, as you may know. And we argued that this is a scaling problem, a technology scaling problem, because we couldn't induce these data corruption Bitflips in older modules from 2008, 2009, newer modules from 2010, and all of the modules from 2012 and 2013 were vulnerable to this effect. Don't get so caught up on error rate over here. It really depends on the type of hammering that you do, etc. This is not the best type of hammering. That's why I'm not going to talk about exact error rates, etc. in most of this talk. Okay, so why is this happening? Essentially, this is electrical disturbance at the very low level. DRAM cells are too close to each other. When you access one cell, when you activate one cell, doing so affects the value in nearby cells because of electrical interference between the cells as well as the wires used for accessing the cells. There are actually very interesting low-level effects over here. We cannot perfectly model it at the device level either. So we actually are looking at methods of modeling it using different techniques right now at the very low level. But I give this example as an intuition. When you activate or apply high voltage to a row, an adjacent row gets slightly activated as well. And there are vulnerable cells in the slightly activated row. They lose a little bit of charge. If RowHammer activation happens enough times, charge in such cells get drained. And if you do not refresh the cells before you lose the data below a threshold, as a result, you basically get data corruption. You cannot read the correct data anymore because charge gets depleted too much. And this sort of device level or logic level issue has large implications on the higher level. Can you see my pointer, by the way? No, okay, interesting. I don't know why, but okay. I'll try not to use my pointer then. I don't know how to make it work. Maybe I'm using another screen. Okay. Okay, so basically, these bitflips get directly exposed to the programming language because data structures on DRAM, and if you get a bitflip in DRAM, they directly affect your data structures essentially. Okay, so we also released this program where we were able to induce errors in real machines. This is only a 6-line x86 program. You can actually make it more optimized. What this program does is it avoids cache hits, it avoids row hits. It basically ping-pongs activates to X and Y like this in DRAM, and if the chip is vulnerable, hopefully you'll get bitflips. And later work from in this paper, we showed that actually if you sandwich one row between X and Y, you get more bitflips. And later work from Google and others have exploited that using double-sided row hammering. So if you this is where attack the hammering patterns actually matters. If you sandwich one row, you get a lot more bitflips. And there are other hammering patterns that are actually important going into the future, I believe. Okay, so this is a real reliability, security, safety issue. Initially, we demonstrated that with Intel and AMD systems, but there's nothing special about them. All memory controllers today in the world are able to induce RowHammer bitflips, assuming the chips are vulnerable and not protected. Okay, when we actually wrote the paper, we said that as first sentence, memory isolation is a key property of a reliable and secure computing system, and access to one memory address should not have unintended side effects on data stored in other addresses. I still strongly believe that we should really prevent this sort of bitflips. We should not rely on basically correcting them afterwards. We should really prevent data corruption because that could lead to a lot of issues, not just in security, but also general robustness. And in the paper, we said that basically someone can hijack your computer if you actually develop this into a security attack. And these good folks from Google Project Zero actually showed exactly that. You may be familiar with this work. I directly copied and pasted from their blog post. They actually have a beautiful black hat presentation as well. They basically said they replicated the issue on some laptops, and they were able to induce bitflips on these laptops. And they developed two types of attacks. One is a virtual machine type of attack that basically takes over the Google native client. The other one takes over x86 Linux using a user-level process. Essentially, the basic idea is to corrupt the page table entries, induce bitflips in the page table entries of a process. And these page table entries are going to point to the page table of that process. And if you're able to induce bitflips at the right places or change the pointers in your page table carefully using a mechanism called page table spraying that they develop, you can gain read-write access to all of your physical memory because you can gain write access to your own page table. Essentially, you're circumventing virtual memory isolation because you don't have physical isolation between the DRAM rows or DRAM pages. So this is now known as the DRAM RowHammer vulnerability, and people are making jokes like this. A famous hacker on the internet that says it's like RowHammer is like breaking into an apartment by repeatedly slamming a neighbor's door until the vibrations open the door you were after. I like this analogy. So if you're stuck in that room over there in Zurich, don't worry. If the door is locked, stop banging on the walls, and if the RowHammer effect is in place, maybe you'll be able to magically open some door. Okay, so there are a lot of interesting works that have ensued, and I don't have time to go over all of these. There are a lot of security works. People showed that you could, using RowHammer bitflips, you can gain unrestricted access to systems of website visitors by exploiting this through the JavaScript. This is a beautiful paper that basically shows that you could take over an Android system by exploiting the deterministic memory allocation patterns in the Android operating system. Again, I don't have time to go over it. There are a lot of interesting things that people have done. People can exploit these attacks using GPUs. People can do this through remote direct memory access in data centers, for example. And even if you cannot take over a system, people have shown that you could break confidentiality. And using RowHammer bitflips, you could actually leak private data, which is interesting. And more recently, people have been looking at neural networks and looking at bitflip attacks on neural networks. And they've shown that using RowHammer, you could actually reduce the accuracy of an otherwise reasonably accurate network to very low accuracy levels, essentially make it useless for all practical purposes. Actually, it's worse than useless. It's completely unsafe if this is used in some safety critical system, like a self-driving car. And people have been drawing pictures like this. So there's a lot to talk about over here. I don't have time to talk about it a lot. We have a lot of papers that have been published. I will mention some interesting directions over here. First of all, I think I will mention some basic understanding we developed, and then I will mention the importance of this because we really need to understand this problem better because the solutions actually rely on understanding this better. So in the original paper, we did a lot of studies using our infrastructure. We tested more than 120 modules, and we have a lot of results. I will mention 3 of these over here. One is logical versus physical adjacency. So if you look at the aggressor row and the victim row, from the perspective of the memory controller, what is the distance in terms of the logical addresses, logical row addresses? Most of the time, they're logically adjacent, again, from the perspective of the memory controller. But there are some cases where the addresses are not adjacent to each other. Now, we hypothesize that this is because there's some internal remapping going on in the DRAM chips that's not exposed to the memory controller. So if the memory controller actually wants to have a solution internally, it needs to take into account these non-adjacencies that happen in the address remapping. And this is a problem in memory controller-based solutions because DRAM and the memory controller don't have a great interface between them. As a result, memory controller or the operating system doesn't know about the address mappings. If you want to have a solution at the system level, you need to deal with these physical non-adjacencies, or sorry, logical non-adjacencies. Okay, we can talk about that more. The other study that we did with real chips is the access interval. So if you actually reduce the access interval of hammering, or increase the access interval of hammering, you can get rid of errors. This is expected because you can fit fewer number of hammerings into a refresh interval. As a result, you may not be able to flip the bits. But unfortunately, you need to increase the access interval too much to get rid of all of the errors. And this is now working, the technology is working against us today, as I will show you. The other lever that you have is the refresh interval. So if you actually increase the refreshes, you can reduce the number of actuations you can fit within a refresh interval. And as a result, you can get rid of all of the errors. In our paper, we showed that you have to increase the refresh rate by 7x to get rid of every single error. And this is exactly what we don't want to do. Basically, this is very bad for energy and performance. And remember that our initial goal when we built this infrastructure was to get rid of refreshes as much as possible. So RowHammer works, getting rid of RowHammer is actually relatively easy if you actually increase the refreshes greatly. Okay, data patterns is interesting, and different data patterns cause different sorts of coupling. And you can see that data patterns that cause a lot more coupling can lead to a lot more errors over here. And there's a lot of investigation that's going on right now as well. So there are a lot of other results over here. One of the most important ones over here is actually errors are repeatable. If a cell is vulnerable, it's going to be vulnerable again and again and again. Basically, you're able to predictably induce bit flips in a cell over and over. Error correction actually doesn't work very well. It's at least simple error correction because you get a lot of errors per cache line, and this is increasing. And we talked about double-sided hammering. So there's a lot more I can talk about. I don't have time, but I'm going to mention some of the other studies soon in a little bit. So I will talk about what has happened more recently also between 2020 and 2023. We have revisited RowHammer. It's getting much worse. There's actually many dimensions, so we need to understand it more. And there are a lot of effects like voltage, etc., that we don't have time to talk about. And this happens with HBM chips also. HBM chips are as vulnerable, and we are studying this in more detail. Now, before I go into a little bit more detail on characterization, let me talk a little bit about solutions. We're going to revisit, we're going to kind of swap between solutions and characterization in this talk. So when you discover such a type of effect, and you need to develop solutions immediately in the field. And also, you should think about longer term. Immediately, unfortunately, we don't have a lot at our hands, at least at the time. And I believe still we don't have a lot at our hands. Basically, we want to protect the vulnerable DRAM chips in the field. We have limited possibilities. In the longer term, we actually can design the DRAM chips to be much more secure, etc. So this is a general, this doesn't cover all of the solutions, but this talks about a bunch of solution approaches, in my view. Building more robust DRAM chips using better materials, better isolation, etc. I think this is difficult, so I'm going to dismiss this for now. We can talk about it if you want. Error correcting codes is very difficult. I think it's very expensive. Error correcting codes are a good solution for bit flips whose reasons you don't know. Here we know the reason exactly. So error correcting codes are actually a huge waste, and they're expensive, as we will discuss. Increasing the refresh rate, unfortunately, is very expensive. Physical isolation could be a solution, but it comes at a cost. It's expensive usually. So I think, in my opinion, we're left with two types of solutions. Reactive refresh, meaning you figure out which rows are being hammered, either probabilistically or deterministically, and refresh victim rows that could be vulnerable. Or proactive throttling, again, you figure out which rows are potentially being hammered and throttle accesses to those rows so that you don't actually cause bit flips in some vulnerable rows that are around them. And maybe a combination of this is interesting. Okay, so but even these solutions actually come at a cost of interesting trade-off space. You trade off between cost, performance, power, complexity, and hopefully not robustness, because if you actually add the security issue, security as a trade-off space, you can always have better performance at the expense of security, of course. So what did industry do initially? Basically, they increased the memory refresh rates because that was the only programmability that we had in the memory controller. And this is Apple. I like quoting Apple over here because they cite our paper and Google's work over here. So our solution, initial solution to this problem was actually very simple. This doesn't work right now because RowHammer has become much worse. Essentially, after closing a row, you activate one or both of its neighbors with a very low probability. And if you do this, you get a pretty good reliability guarantee. It's a probabilistic solution. And if you're paranoid, you can adjust the value of P and vary the strength of the protection. And we showed that this is actually very stateless. It's very, very low cost. It's still the lowest cost solution that we have. Is there a question? No. Okay, feel free to stop me. Otherwise, I can actually go. I can actually hammer the audience with going fast. It's high bandwidth memory, right? Okay, so basically, this is variants of this are actually implemented in DRAM chip and memory controllers. I will briefly mention these. But as I said, this is a solution that doesn't work alone by itself today. And I believe it's very hard to make it work together with other solutions also. Now, that said, I think this was a step in the right direction. What Intel did was actually adopt a similar solution. Not exactly how we envisioned it. They actually enabled this in the BIOS. So in the BIOS, for example, in some Intel systems, you could choose your RowHammer solution. You could either choose hardware RowHammer protection and 2x refresh. And if you go to hardware RowHammer protection, you basically pick your activation probability over here. So it's a variant of a probabilistic solution that has similarities to Para. Okay, so I think this is an example of a slightly intelligent controller that does some probabilistic activation to cover for this effect. I believe we need a lot more of these. We need a lot more intelligent controllers to solve this sort of issues because these issues are going to get much worse, as I will describe. Now, I will also mention that we have been doing a lot of work on NAND flash memory, and we have intelligent controllers on the storage side. On the storage side, these controllers actually try to account for many, many different types of effects, and they're quite intelligent in how they set the voltages, for example, how they handle read disturb phenomenon that we've also studied in flash, etc. So we know how to build these controllers, but not for DRAM. I think we need to actually spend a lot of time for building controllers for DRAM and how to make it actually software accessible in a secure way. Okay, so in my opinion, going forward, we have two major directions. We need to understand RowHammer much better. There are many effects that still need to be rigorously examined: aging, environmental conditions, memory access patterns, control and system design decisions. They all affect your vulnerability. And we don't quite understand all of them. I'm going to show you some examples in a little bit. And we need to solve RowHammer. We need to have flexible and efficient solutions that can be patchable, reconfigurable, or programmable in the field, because there may be other effects that we have not considered when we actually build these solutions. And I believe co-architecting system and memory is important, because once you actually, even when you securely solve this problem, you usually turn it into a performance problem or denial of service problem. And I think it's important to recognize that and provide solutions to that. Okay, so now let me go into what has happened in 2020, 2023. So when we actually did this work, we said that, oh, industry should solve this problem, and here are some solutions, and then we actually moved on. But unfortunately, industry did not completely solve this problem, so we actually wanted to revisit RowHammer, and this is a paper that we published in ISCA 2020. I will not go into a lot of detail. Basically, we did a lot of studies on many, many more chips this time, and we found out that new DRAM chips are much more vulnerable. More bit flips are happening earlier. And there's some DRAM chips where the weakest cells fail only after 4,800 hammers. This is double-sided, so you actually are around 9,600 hammerings. Now, this number was around 139,000 in 2014 when we did the original studies. So basically, the vulnerability became about an order of magnitude worse over the course of 5 or 6 or 7 years, however you count it. Basically, newer chips are much more vulnerable, and we basically studied the existing mitigation mechanisms at the time, and we basically showed that they're not scalable at future technology nodes if RowHammer vulnerability is going to get worse over time like this. So again, I don't have time to cover all of these, but we tested a lot of chips, and we showed that newer chips are much more vulnerable. Bit flip rates are increased when you go from old DDR4 to new DDR4, for example. And Bitflips happened earlier with smaller hammer counts, smaller number of activation counts, essentially. And if you actually look at the hammer count over here on the left, on the x-axis, and look at different solutions and performance impact of different solutions, for hammer counts, we're marching from left to right when we actually advance the technology generations. And as we march from left to right, different solutions become much more expensive in terms of performance. For example, increasing the refresh rate is a terrible solution, as you can see over here. Probabilistic adjacent row activation that I described becomes terrible at low hammer counts. And ideal solution, even ideal solution degrades at low hammer counts. And we're marching toward these hammer counts, in my opinion. If we get Bitflips after 100 activations in DRAM, now benign applications are actually going to cause these Bitflips. We're doing a lot of studies on this, and some actually papers have shown this as well. So how do you actually deal with benign applications causing Bitflips or potentially causing Bitflips? Okay, let me talk a little bit about RowHammer characteristics very quickly. I don't have time again to cover everything over here, but this is more to demonstrate that we don't quite understand everything. Essentially, this paper, Micro 2021, we studied temperature, aggressor row activation time. I'm going to talk a lot about this later on, and physical location and victim cells. And basically, we studied again in a number of chips, and we found out that we don't quite understand what's happening with temperature. Bitflip is more likely to occur in a bounded range of temperature. There's no strong relationship between RowHammer and temperature. Essentially, it depends on the bit, depends on the temperature range. If the aggressor row is kept active for a longer time, you get more Bitflips. We're going to talk about that. This is the basis of the RowPress issue. And certain physical regions of the DRAM module that's under attack are actually much more vulnerable. So you could actually use all of these from an attacker perspective to build better attacks, and from a defender perspective to build better defenses. And we demonstrate that in the paper. But I think from a defender perspective, we should be more careful, because if you do not take into account some of these effects, we may actually configure a RowHammer defense to refresh adjacent rows, for example, at a particular activation count. But if we didn't take into account some effect, that activation count may actually be lower in practice. As a result, we may not actually protect against RowHammer with a protection that assumes a particular activation count. You can also improve defenses. So if you actually know which bits are much more vulnerable in DRAM, you can actually protect those much better and protect the other ones less. We actually have a paper coming up at HPCA that looks at this in a lot more detail right now. Okay, so there's more RowHammer analysis that you can do, and I could talk a lot more about this. Word line voltage is quite interesting, because when you actually activate a row, you're applying high voltage, and we wanted to study the effect. Unfortunately, by changing the word line voltage, you don't have a silver bullet. You need to build a lot of infrastructure to study these things, and which we did. But you can reduce the RowHammer vulnerability, yes, but not enough to actually do this as a solution. Okay, so there's more. And as I said, this happens in HBM chips as well, and I'm happy to talk about this because we don't have time. Now let's talk about solutions again. Let's talk about the solution directions. As I said, we expected the industry to solve this problem. Industry meaning the DRAM industry or memory control industry, and there were clearly solutions in the right direction, in our opinion, like having memory controllers that are doing probabilistic activation is a solution in the right direction. We need to build that to be much better, of course, going into the future. Unfortunately, what happened in industry was something that's not good for security, in my opinion. Basically, DRAM manufacturers asserted that they solved the RowHammer problem with DDR4, and everybody somehow magically believed that. That sounds great. Now, of course, as a researcher, you question these things. So we collaborated with good folks from Vrije University of Amsterdam to show that this is not the case. Essentially, DRAM chips that are advertised to be secure are essentially not secure. So in JEDEC, there were a lot of discussions that they introduced this target row refresh, which is not defined in a concrete way. But memory controller or the DRAM chip can actually refresh target rows, let's say. And it's not clear what the solution was. So we had to reverse engineer the solution. So we introduced a new attack based on what we reverse engineered using our FPGA-based infrastructure. The idea in this attack is to hammer many rows to bypass the internal target row refresh mitigations. And these mitigations usually work internally in the DRAM chip by detecting some rows that are activated a lot. And to be able to do so, they actually use some proprietary tables that are not exposed outside. If you somehow overflow those tables, you could actually put the DRAM chip back to square one. Essentially, it's not detecting which rows are frequently activated anymore. That's what we did, basically. To be able to do that, we reverse engineer these implementations, and we actually provide an automatic tool that can effectively create these attacks. And these results were really scratching the surface. Just to give you an idea, this is a 3-sided hammering pattern. This is a 4-sided hammering pattern. Normally, a double-sided hammering pattern, in the absence of any solution, should work the best, because given other effects that we don't understand in a pure RowHammer attack. But if you actually do a 4-sided RowHammer pattern, and if the DRAM chip internally has a table for 3, for example, you overflow that table. And these are real results from the real chips. For example, you don't get Bitflips until 9-sided RowHammering patterns over here, but after 9-sided, you get Bitflips. And we basically showed that in some cases, you need 19-sided Bitflips to get the most Bitflips, etc. Okay, and then we actually showed that you could actually do this in phones, and you could actually basically circumvent all of these protections. So basically, trespass showed that RowHammer is still an open problem, and security by obscurity is likely not a good solution. And I still believe that, actually. And I think we're still going through the same path, unfortunately, as we will discuss with what's happening in DRAM. So this paper, along with the revisiting RowHammer, caused a lot of, let's say, churn. And with the push from, let's say, hyperscalers like Microsoft and Google, JEDEC finally released some, or reformed its working group on RowHammer mitigation. And you can read some of the, let's say, high-level things that they have put. But actually, you can actually completely reverse engineer these solutions if you put some effort. And that's what we did in this paper. I'm not going to talk about this in detail. But basically, in this work, using our FPGA-based infrastructure, we use data retention failures as a side channel of when a DRAM chip is internally refreshing adjacent rows. So if you know the retention time of a row, you expect a bit flip will happen if you don't refresh that row. But based on some RowHammer pattern, if the DRAM chip internally refreshes that row, you know that that row is not refreshed, even though it should get bit flips. So you have a side channel right now based on the retention time profiling that you've done. So with the infrastructure that we built, we understood the retention time failures and RowHammer failures, and we can actually combine them to understand what's going on inside a DRAM chip. Actually, with this methodology, you can uncover a lot of things in the DRAM chip, depending on how much time you have. You can uncover the operation of refresh, regular refresh as well, and we did some of that too. But basically, if you do this, you can uncover what's going on underneath. And different manufacturers have different types of solutions, as you can see. Some of them use counters to detect aggressor rows. Some of them use some sampling, random sampling, like probabilistic adjacent activation. Aggressor capacities are different. Whether they do per bank or not per bank is different, etc. Again, I'm not going to bore you with this. The key takeaway is you can induce RowHammer bit flips on all modules, essentially, if you understand what's going on inside the DRAM chip. And again, ECC doesn't work because in some cases, you get 7 bit flips in an ECC word, for example. Of course, ECC would work if you actually have a much stronger ECC, which is much more expensive. Okay, so there's clearly interest in hyperscalers in this as well. Google developed this beautiful attack, in my opinion. I will mention this relatively quickly, but basically, these folks show that RowHammer effects happens across multiple rows. So if you have an aggressor like this, and if you hammer it many times, okay, sorry, you don't see my you don't see my thing. If you look at the aggressor in the middle, aggressor A, if you can hammer it many times, and if you hammer aggressor B a very few times, you get bit flips on the victim C over here. Why is this interesting? The interesting thing is if you have a solution that refreshes aggressor B because you're hammering aggressor A, now the solution itself becomes an attack on victim C. So unfortunately, you need to deal with this sort of effects, this sort of physical non-adjacency effects as well. And they publish this at using security. Okay, so let me talk a little bit more about solutions now that we've talked about some more attacks and characterization. So this is another solution that doesn't work if you go to very low RowHammer thresholds. Essentially, in this work, we wanted to be scalable with worsening RowHammer vulnerability, and we were better than prior work at the time. And we wanted to be completely compatible with commodity DRAM chips. So this was a memory controller-based solution. The idea is throttling. Basically, you have some bloom filters in the memory controller. These bloom filters detect which rows are being activated a lot. And if you figure out which rows, some rows that are being activated a lot, throttle the accesses. And we have a security proof that shows how much you should throttle, when you should start throttling, etc., a particular row. And if you actually do this, you can optionally inform the system software about the attack. And with very high likelihood, we can detect attacks. We have a RowHammer likelihood index that characterizes different programs this way. Now, this, I think, could be a part of the solution. Unfortunately, the area and energy of this becomes very high as you go to lower RowHammer thresholds like 100 or 500 even. But this is another example of an intelligent controller that I've been kind of mentioning. It became more intelligent, as you can see over here. So I think solution approaches need to become more intelligent going into the future. I can talk a lot about solutions, but I'm not going to do that because we don't have time. I'm going to talk about what industry has finally released and publicly acknowledged. This is ISSCC, that's the Major Circuits Conference this February. SK Hynix published this paper. This is really the first paper that is published by a major DRAM manufacturer on RowHammer. And they basically described a variety of solutions that they employ. Some of them are probabilistic, like we've discussed. A lot of these are based on what has been discussed in literature in the past. But basically, they have an intelligent control inside the DRAM chip now. For each memory cell, they have some counters. This is one solution that they discussed. These counters count the activations. And if the activations are greater than some threshold, they basically refresh something. They don't say exactly what. It's actually very nebulous. So it's another approach that's a little bit more obscure. So I believe this actually is still vulnerable under some conditions, and those conditions need to be examined. Okay, Samsung, of course, released their own solutions with this paper as well. If you're interested, you can take a look. So the question is, are we now Bitflip free today and beyond? I don't believe so. Now I'm going to talk about very briefly a paper that we have published in ISCA this year, and then we're going to conclude at the end. So essentially, we wanted to understand other Bitflips, other type of Bitflip mechanism. And RowPress is a new disturbance phenomenon that can be coupled with RowHammer. It's different from the RowHammer vulnerability. So we demonstrate using a user-level program as well as our infrastructure, so we can get Bitflips in real chips. And there could be effective solutions, but they come at a cost. Again, performance, additional area, complexity. So what is the idea? Basically, if you keep a DRAM row open for a long time, this causes Bitflips in adjacent rows. These Bitflips do not require many row activations. Only one activation enough in some cases. This is when you violate the timing parameters a lot, yes. But this is fascinating because when you activate one row, wait for 30 milliseconds, and Bitflips happen in adjacent rows, not this row, adjacent rows. Okay, so this is different from RowHammer. Again, I don't have time to talk about it, but basically the way I think about these things is, are there cases, you build this fence, that's kind of a RowHammer solution, but are there cases where you can go around this fence easily? And this is one of those cases, in my opinion. So basically, RowHammer activates an aggressor row many, many times, as much as possible. RowPress basically activates a row, but keeps it open for a long time. As a result, you can reduce the number of activations greatly. And if your solution is relying on number of activations, and if you set the solution to account for, let's say, 40K activations, now your solution is useless, basically. Okay, so we actually built more infrastructure to study this. We studied, again, major manufacturers, and we showed that RowPress significantly amplifies DRAM vulnerability to read disturbance, and is a different underlying mechanism. So let me quickly talk about this over here. This is RowHammer over here. If you keep the row open 36 nanoseconds, you need to do this many activations in real chips. It's 10 to the 4, 10 to the 5, as you can see. But if you keep the row open a little bit longer, these are valid in JEDEC standard, you can reduce the activation count greatly by 1 to 2 orders of magnitude. Now, 30 milliseconds is violating the standard, but it's interesting to examine fundamentally. Okay. So this is actually very different from RowHammer. As temperature increases, this effect becomes worse. We cannot say something like this for RowHammer. Also, a different set of cells are affected compared to RowHammer. And this behaves differently as access pattern and temperature changes, but I don't have time to talk about those. So we showed the proof of concept RowPress program that keeps a row open for a longer period of time on an Intel system using a Samsung module that's protected with RowHammer mitigation. You need to do a lot of tricks to actually align refreshes with accesses, etc., like people do in RowHammer today. But the basic idea is to access different cache blocks in a row so that you ensure that or hope that the memory controller keeps the row open as long as possible. And we've seen that actually you could do that by keeping, for example, 32 cache blocks open. You can get Bitflips, whereas you cannot get Bitflips otherwise, let's say, if you keep a smaller number of cache blocks open. So this is a vulnerability in real systems. It's clearly this is not an attack, but this could be developed into an attack, in our opinion. So how do you mitigate this? Basically, there are a bunch of solutions that we discussed. I'm going to mention one thing. I believe you need to limit the maximum row open time to a lower value than what we actually do today in our systems. That's not enough. We need to configure the RowHammer mitigation to account for the RowPress-induced reduction in activation count at that particular row open time. So your RowHammer mitigation now needs to be a lot more aggressive, basically. This introduces additional overhead in terms of performance. We show that it's relatively small, but it really depends in the end. relatively small, depends on what the application you're looking at and what kind of system configuration you're looking at. So basically, it's going to get worse. And if you're interested, you can download it and use it on your own. Okay, I believe there's more to come. So that's why I think we need to understand Bitflips and hardware errors in general, and we need to develop solutions that can actually, for example, if we had a programmable memory controller, we believe you could program the memory controller to account for issues like RowPress once you actually had the RowHammer solutions in place in that controller. So this is the sort of flexibility that we're quite interested in. Okay, how much time do we have left?
I think we only have 2 minutes left before the next presentation. So
okay. So I think I'm not going to talk about all of these. Maybe I should stop here and conclude. Let me go to the final slide over here. Okay, maybe I should talk about this. So I think basically we will have Bitflips. This is real infrastructure. Human beings have been building bridges for thousands of years, and we still haven't gotten it right. I don't believe we're going to get computing robustness right, but we can actually develop solutions like intelligent memory that's much more applicable than in heavy infrastructure like bridges. So going forward, I think we need to do that more. So I'm going to conclude over here since we don't have time. But these slides, I'm happy to make it available. You can take a look at it. I'm happy to take questions right now.
Thank you.
If you're asking questions from the room in Zurich, please use the microphone so that people on GBC can hear you.
Oh, hello. Thank you for your talk. Should I say I'm Johannes from ETH? So I have a question. So like DDR4 was like released in 2014. So this is like before we thought of RowHammer as like a security issue or like a security issue. We thought maybe more about it as a reliability issue. And a lot of these papers that we see are like always about DDR4. And could it be that it's difficult to mitigate RowHammer in DDR4 because of the specification that you need to be like compatible with a old non-RowHammer aware specification? And what do you think about the DRAM that has actually been designed RowHammer aware like DDR5?
Well, I think I don't think DDR4 is RowHammer unaware, right? Because the TRR, for example, was introduced in DDR4, and that's the reason why TRR was introduced was RowHammer, right? And DDR4 also evolved over time. People have improved the mitigations internally as well. So it's certainly it's true that DDR5 certainly it's true that DRAM manufacturers and memory controller manufacturers are more aware of the issue, and it's going to be more and more difficult to induce these Bitflips, especially if you just consider RowHammer, right? I think RowHammer, we know a lot about it, but we don't know the boundary conditions, in my opinion, as much. That's why I think other types of Bitflips are going to be interesting. And boundary conditions under which perhaps RowHammer gets much worse in a way that's not accounted for inside the memory controller or the DRAM chip will also introduce a lot of issues, in my opinion. So I think it's I don't think it's an issue of DDR4 versus DDR5. Clearly, things are going to get better and specifications will become better over time, and people will provide much more solutions. But I believe what we are missing, what we don't know, is going to hurt us a lot more going into the future. And that's why I think RowPress is, for example, quite interesting. I believe there are other issues out there that we don't know, but that will hurt us because we don't take into account. We don't have an infrastructure that doesn't take them into account well.
Thank you.
Hi, this is Andrew Bauman. It seems like the underlying problem here is that everybody wants denser, cheaper, faster DRAM. And that has a fundamental trade-off with reliability. But when we buy DRAM, we don't really see metrics for the reliability aspect, except for every few years, you guys look at them and everything's a disaster. So can we come up with a metric that I can look at when I'm buying some DRAM that tells me how reliable is this DRAM versus that one, and I can make that trade-off as well?
Yeah. I mean, that's a very good point. Basically, we've been arguing for something similar. I'll try to get back to if I can find it over here. But basically, I think we need to be a lot more transparent about reliability. I don't have the paper over here. Sorry. It's okay. It's over here. I think as an industry, The downside over here, yes, I think it's good to have reliability specifications, but unfortunately, this is not good for the business of the DRAM manufacturers. They've been paranoid about people figuring out the different reliability characteristics internally for multiple reasons. One is it's not good for business if they actually lose business, and the second is basically you would lose important. You basically someone can figure out what they're doing internally. I believe we're past that point. We need to change the interface in DRAM and enable something to the DRAM manufacturer so they can actually improve reliability on their own. I think one of the issues that we have is the interface between the memory controller and the system and the DRAM is very inflexible. As a result, anything that happens in DRAM gets directly exposed to the memory controller or the system. So if we somehow have a better interface, we can perhaps also come up with better ways of improving reliability inside the DRAM. So I agree with you completely, but I don't think it's going to happen immediately because clearly this is at the core of the DRAM manufacturer's business. They're not going to reveal all of these numbers just because people ask for them.
Matthias Peyer, EPFL. Very amazing speed run across all the RowHammer issues of the last 10 years. Quick question. I wondered, assuming something like Andrew mentioned, if you would have performance specification for individual DRAM cells, how much could you push the analysis or protection to a trusted either operating system or hypervisor to slow down kind of untrusted software? You see a lot of cache misses. There's performance monitors everywhere, and you could imagine some additional like performance counters to at least detect any ongoing attacks. And maybe there's some false positives where you slow down some applications, but in general, it looks extremely noisy, or any of these attacks look noisy. Mm-hmm. And I'm from a security background. I'm aware that normally detection is always has issues, but I wanted to hear the expert opinion.
Yeah. No, that's a great point. So and people have proposed those that sort of things. Anvil, for example, and other sort of solutions. They use performance counters to detect, let's say, many row activations, etc. They can be improved. So there are papers and literature. I think it's good to look at them for sure. And these could be first indicator of a potential attack. At the system level, you collect information. And maybe the downside I see is unless, so those solutions work nicely if the activation counts are very large. But if the activation count goes to, let's say, 100 or 25, for example, in our recent papers, we're looking at 50. And if you get a bit flip, after 50 activations, that's beyond the domain of system software at this point because the granularity is too small at that point. So I think, in my opinion, actually, and in many of the works, we argue that this needs to be solved across the stack. There needs to be some solutions in the hardware, but hardware cannot completely solve all of the problems. It can convert the problems into a denial of service problem, for example. So if you actually have solutions, mechanisms to monitor at the system level, I think you can actually have a much better solution overall. But I don't think that can be the only solution, unfortunately.
Thank you.
All right. Sorry, we're out of time. Time to go to the next presentation. Thanks, Professor Mutlu, for the RowHammer presentation.
Thank you.